Why do we need gravitons when gravity is not a force? This is a question from Quora.com. Imagine asking such a question. We've come a very long way with gravity since the days of Aristotle. Aristotle, and this idea lasted for over a long time, 1,000 years, said that bigger things will fall faster than smaller things, and it made logical sense. Then Leonardo da Vinci noticed that things, by observing without experimentation, that things fall faster and faster. Like first time it would go once, in the second unit of time it would go twice that distance, then third time 3 times the distance of the first one. But still Leonardo da Vinci believed in the idea of Aristotle. Then came Galileo, changed all things for us. All things fall at the same speed, all things fall at the same speed. No matter how big it is, no matter how small it is, they are pulled by gravity at the same rate. Absolutely fantastic. And, the sad thing about it, there's this video going around TikTok, Instagram, this guy, he drops some water in a water bottle and says, see, the water doesn't fall out, that's Einstein, we understand that because of Einstein. No. Doesn't matter how eloquent you are, we understand that because of Galileo. And we understand Newton's first law because of Galileo, not because of Newton. Stuff like that, that's how science is, Before I did my experiments on magnetism, I'd come to the conclusion that everything's made out of the same stuff, by looking at all the experiments around. I'm reading other people's experiments, by looking at, where stuff is coming from, how it's all balancing out. So I understood it's all made out of the same stuff. And this is before I did my experiments, So now I had not much. Then I thought I'd give gravity a thought. What is gravity? Given that perhaps I have enough information now that I know that everything is made up of the same stuff, maybe I can tackle this question, gravity, So let me read something for you. The hypothesis I came up with was called Gonke gravity and particle relationships. Let me read for you the conclusions. This is a theoretical paper on how Gonke is ether. Gonke deals with all the knowledge we can know. Ether, a term that came long before Gonke in terms of science, ether came around 4,000 years ago. So on how ether can get into relationships and we get particles. The existence of Gonke is of no doubt. All particles are made up of the same stuff. This same stuff must get into a relationship. This can only be done with another agent we have called V2, which very well could be gravity, meaning gravity is independent of the Big Bang and is one of two basic forms of matter, the other being Gonke. This would mean anything with mass has gravity as its basic constituent. I don't like this idea. I don't like it at all. But just to show you, I did tackle gravity before the experiment. Remember, Gonke deals with knowledge and ether deals with physics. I was a very lucky man that the when I was experimenting with magnetism, it organized into a wave, That means confirming there's something finer. So I was very confident before, even before the experiments, there was just too much evidence for something finer, Because I'm just saying, what do I think of gravity now? Well, since I did those experiments and understood magnetism, a lot clicked to me. A lot clicked to me. So we have this. This is a ball, big mass. It has then there's this other big ball, big mass. This big ball, big mass is going around this one. Or maybe that's too big, Let's make it half the size. And this is going around this one. We say this is attracting this. No, they're both attracting each other. That means there is a point where there's imbalance, and the attraction, the balance is right there. That's all what is happening. It's a quantum phenomenon. If it's here, to push back. If it's here, it will come here, to that exact spot, relating to its mass. They're both attracting each other. Magnetism, what we have in magnetism is they're pushing each other away. When they're similar. They're pushing each other away when they're similar, and they're annihilating each other when they're different. This is quantum phenomena. We use observation and experiments before and make a logical pattern. So this, whatever's radiating from here, which doesn't seem to affect all mass, it doesn't affect neutrinos. And what is radiating here in terms of attraction of the greater mass balances out right there. The waves cancel each other somewhere right there. Then it doesn't fall in, it doesn't fall out, because the waves are canceling each other. Or balancing each other, should I say. Because balance, a fine balance. So you have to be a quantum physicist. I accept what's happening. Over here, there's attraction. So it looks like North and South Pole, but it isn't. We're dealing with gravity now. Because right there, there's repulsion. But we're dealing with gravity. So we have this thing that understands on its own it must balance. Like all other quantum phenomena, there's a balance of whatever's radiating from both of them. And when there's an imbalance, that's all what's happening. Then you think in terms of quantum phenomena, you take those equations, probably talk about momentum and you add stuff, that's all. But you think of it as waves balancing, particles balancing each other at some point. That's what I think of gravitons. It's a force, definitely a force, but I don't think it comes from the funny thing is, I read some guys in string theory saying gravity comes from another dimension. Like I'm thinking it's coming from the ether. It's the ether's got its far from that. No, here it's just waves balancing each other. It's not from the ether, it's not from other dimension. That's what I have to say. And when we talk of waves balancing, then you can start adding in Einstein's equivalence language.